Alright, gang, here we go. Chem 2 Unit 12. Now we're going to start getting into the nitty-grittiness of entropy and what it means for us as chemists. All right, so let's remember we've been talking about entropy, and we've got the understanding now that entropy is really just a measure of the disorder of a system, right? And so we kind of talked in the last video about how we can keep track of microstates in order to kind of get an idea of what the actual entropy value is and what that means for our system and so on. This current unit, this part that you're going to watch now, this video, is really about by the end of this part, you should be able to look at a system and how it changes and be able to determine whether or not your entropy is increasing, decreasing, or essentially remaining exactly the same. So in order to do that, we're going to look at three different things that really play a large role in determining what happens to our entropy. All right, the first one is volume. So think about this. If we increase the volume of our system, that means that there are many more positions, okay, for our molecules to be in. And so if there's more positions for our molecules to be in, then that means that there's more disorder available. Or, to use kind of what we learned last video, there are more microstates. And so therefore, because there's more possible positions, there's more microstates, and then therefore, because remember we learned that the entropy is equal to K times the natural log of W, so if our number of microstates goes up, this W, that means that we'll have an increase in entropy. Okay, so increasing volume increases entropy, and then therefore decreasing volume would also decrease entropy. All right, the next guy here says if we increase temperature, the average kinetic energy would increase. Well, that makes sense, right? Because temperature is a measure of the average kinetic energy. So therefore, this results in a greater distribution of molecular speeds, right? So remember our Boltzmann curves. Here's our Boltzmann curves. If we are at a given, so here's our kinetic energy, number of particles, right? If we're at a given temperature, our Boltzmann distribution looks something like this, kind of tails off to the right. If we increase the temperature, right? Well, maybe I'll just draw it on the same one. And if we increase temperature, we still have some of them that are moving essentially zero, but the average is going to get higher. So we'll have our curve will look something like this, right? And we can see that there's more opportunities or more different microstates worth of kinetic energy that our molecules can have. Therefore, more microstates, again, more kinetic energy, more entropy. So many words, so little time. Okay. So anyway, and this goes under the same idea. If we increase temperature, our entropy will go up. If we decrease temperature, our kinetic energy, our entropy goes down. All right. Last thing we'll look at is molecular motions. Remember, so essentially those first two, we're talking about where our molecule was in space, right? Different available microstates within space. Now, if we think about, well, what is it doing within itself or with respect to with each other? Okay, and so molecules have different types of motion that they can undergo. There's translational motion, where they're able to slide up and down, left, right. Think translation when you were in geometry. Vibrational. Okay, and there's lots of different vibrationals things. Like once you get farther into chemistry, vibrational stuff is actually pretty interesting. It's used to help identify different molecules through IR spectrum and NMR and stuff like that. Kind of cool. All right, and then the last one would be rotational, right? So those are the three main types of motion. Your molecule can rotate in space, it can slide around in three-dimensional space, and it can also vibrate against its own bonds, right? You can have those vibrations going on. So therefore, each molecule can have each of those things can have a different value. So therefore, each of those is a different microstate. And then also, because if you have more atoms or more molecules, then therefore you have more microstates available to you as well. So molecules that are very, very big, like polymers, have lots of microstates available because they have lots of atoms, which means there's lots of rotations. There's rotations in space and also in regard to each other. They can fold in over themselves, right? We've all seen those giant proteins. Or you can have them like vibrating against each other inside their individual bonds, all right? So therefore, the number of microstates is really affected by these three things. Okay, so the entropy tend to increase, okay, with these three things as they increase. So when temperature increases, your entropy increases. When volume increases, your entropy increases. And when the just pure number of independently moving molecules increases, your entropy also increases. All right, and then what's really handy is the converse is also true. If one of those decrease, your entropy also tends to decrease. Now, you may be wondering to yourself, well, Mr. McLeod, what if something is increasing and the other one is decreasing? Well, then you're kind of hosed. No, I'm just teasing. Then you got to have a little bit more information. You have to do a little bit of calculation to figure it out. But for now, we're just going to stick with that qualitative, being able to look at a couple things, all right, and be able to figure it out. So we're going to look at a couple practice problems here in a second, kind of give you an idea of what kind of skills you're after. And so here we go. So entropy in physical states, I kind of hinted at this first time I introduced entropy a couple of videos ago, but we're just kind of formalize it now. So if we know entropy is really about keeping track of the number of microstates, which is, one of those microstates that we have to worry about is their position in space. We know that one way to keep track of their microstates is by their state of matter. Okay, gases move around very freely. They ignore their intermolecular forces. They bounce off each other elastically. If we assume both those last two things, if they're ideal gases. All right. Whereas solids are kind of stuck in one place. They form this nice crystal lattice. They can't go anywhere. All right. So anyway, entropy tends to increase as we go from solid to gas. So here's the entropy of a gas is greater than the entropy of the liquid, which is greater than the entropy of the solid. And down here, they just kind of give you a couple of bullet points that you can use to kind of rest your hat on here. So the entropy of your system increases for these processes, right? If your gas gets formed from solids or liquids, or your liquid is formed from a solid, or the number of gas molecules increases during a chemical reaction. So there's a big one right there that's super helpful. All right. Okay, so here we go. So entropy and physical states. So here's ice, liquid, and water vapor. Ice is kind of a funny duck, right? He's kind of a weird duck. Remember, he expands as he freezes. But notice here that there's very orderly, not very disordered. Each one of these water molecules is kind of stuck in space because of those hydrogen bonds it forms. This liquid water is much more free to move around, and then obviously water vapor has much more space to move around. They bounce off each other, so on and so forth. So you're increasing entropy as you go from left to right. Okay. Notice that also as this compound down here, whatever this some ionic thing, whatever, it's got purple and green, positive and negative. As this gets dissolved, dissociated into the water, its entropy also increases. And then finally over here you've got this compound, this this nitrogen monoxide reacting with oxygen to form nitrogen dioxide. You're starting with 3 moles of entropy, or 3 moles of gas here, and you're only getting 2 moles of gas here. So you'd see our entropy would actually be decreasing as you go to the right. All right, and then finally we're going to talk briefly about the third law of thermodynamics. No discussion of thermodynamics would be complete without discussing all 3 laws of thermodynamics. Okay, I'm not quite sure why they kept this thing and this thing. I think it seems like it would make more sense in the previous thing, but whatever. So the entropy, so this is the third law of thermodynamics right here. It says the entropy of a pure crystalline substance at absolute zero is 0. So this is the only time where you can have entropy of 0, meaning that there's only one possible microstate. So think about it this way. If you have a pure crystalline substance and it's at absolute 0, that means it has absolutely nowhere to go, right? It's in this pure crystal structure. It's not vibrating. It's not moving, not doing anything. So all arrangements of those molecules, and it doesn't even matter how many there are, there's only one possible microstate. And that's what it is, because that you're at absolute 0. There's nowhere else for it to be. There's no other possible ways. So therefore, it has one microstate. So if we plug that into that formula we learned last time, where S is equal to K natural log of W, and we plug 1 in for W, well, natural log of 1 is 0, so therefore it's equal to 0. All right. So anyway, so let's talk about these guys here. So we're going to predict the sign of delta S Okay, so essentially we're just after, is entropy increasing or is entropy decreasing? So here for part A, we're going from water liquid to water gas. Well, if we're going from a liquid to gas, we learned earlier that if we go from liquid to gas, then that means our entropy is increasing, so that means we have a positive entropy change. All right. Okay. All right, let's see here. So this next guy here, we have silver ions reacting with chloride ions to form silver chloride. Notice that we're starting with, there's two ions over here. Okay, so two separate things going to one thing. Well, that would indicate that our entropy would decreasing. So we have that going for us, and we also can look at the states of matter. We see that we've got aqueous turning into a solid. Well, these two aqueous things have much more freedom to move because they can move around solution, but as a solid, they're pretty much stuck in one spot. So this has a negative entropy change. All right, here we go. C here. So C, we're going from iron to plus oxygen yields iron oxide, so just reacting here, a little bit of a redox reaction. So we got 4 pieces of solid iron with 3 molecules of gas forming 2 pieces of solid. So we're losing all of our gas and we're losing some of our solid atoms. So therefore we've got less total things and our states of matter are changing. We got a solid and gas going to just a solid. So therefore our entropy would be decreasing for that one as well. All right, and then last one here, it says nitrogen plus oxygen yields 2NO. So therefore, so here we've got so we've got gas going to a gas. Not only that, but there's one gas here and one gas here. 1 and 1 is 2. So this would say, I'd say this has a delta S pretty close to 0. Absolutely no change whatsoever. So I know that's not really, it says positive or negative, but I don't think it would really change as far as what we've learned thus far. Anyway, so that's it for this part here. We're trucking along. We're learning about thermodynamics. Hopefully it's not too confusing. This is probably the most important part that you've got so far, being able to look at a change in a system and be able to determine whether or not your delta S is going up or down. Anyway, do you practice problems? Let me know if you have any questions, and I'll see you on the flip side.